Hello friends, so today we are going to solve the questions from heat and thermodynamics. Total we are going to solve 5 questions from the year 1991, one question from 1992, 2 questions, and from 1993 there are also 2 questions. So total we are going to solve 5 questions. So the first question, it was asked in the year 1991, and it states that 3 moles of an ideal gas Cp7r/2 at pressure Pa and temperature Ta is isothermally expanded to twice its initial volume. It is then compressed at a constant pressure to its original volume. Finally, gas is compressed at a constant volume to its original pressure Pa. Then, based on this, we are having 4, you can say, options, or rather 2 questions. Sketch PV and PT diagrams for the complete process. Calculate the net work done by the gas and net heat supplied to the gas during the complete process. So, in this case, we are given that first of all, we are going to plot the, you can say, PT graph, and it says that it is, first process is basically isothermal. So we are having our, so y-axis, this is our pressure, and x-axis is our temperature, and we start from a point. Let us suppose that a point is our A, and A is having pressure as Pa, volume as Va, and temperature at Ta. And it says that is expanded isothermally so that it becomes twice the initial volume. Okay, and the it is isothermal. So we can plot the isothermal. Let us suppose it start from A, and the second point is our, this point is our B, and here let us suppose the pressure is our Pb, volume its state is our 2 times our initial volume, and temperature is still our Ta. Now it is, you can say, compressed at a constant pressure. So it is compressed at a constant pressure, and let us suppose it reaches a certain point C. And here at point C, our pressure will be Pb because it is a constant pressure, and it says that it comes to the original volume. Original volume is our Va, and temperature is suppose our Tc. And then it is compressed at constant volume to original pressure Pa. Okay, so it is returned back to original A point. Okay, so this is our basically PT, pressure temperature diagram. Okay, so first process is our isothermal from A to B. So you can see our A to B is isothermal, and for that we can write that PA multiplied by VA is equal to our PB multiplied by VB, and VB is our, this is our VB, but it is equivalent to our twice of A. So we can write this as our PB into twice of VA, and this VA and VA cancels out, so we get that pressure at B is equal to half that of pressure at A. Now we come to B to C. From B to C, our pressure is same, so we can say this is our isobaric, and isobaric compression. And for that we can write that our VB upon TB is equal to our VC upon TC, okay? And VB is our twice of VA, so we get twice of VA upon TB is our TB is nothing but our TA, so we can separate this as our TA will be equal to, now our volume at C is nothing but our VA, so this comes as VA, and we have temperature as our TC, okay? And from here this VA and VA cancels out, so we get that our TC is equal to TA by 2. And then we have from C to A. From C to A, and this is our, it is given as volume is constant. Volume is constant. Therefore, we can write that our PC upon TC is equal to PA upon TA, and our PC is nothing but equal to PB, so this is our PB and this is equal to our PC. So we can write PB upon TC is equal to PA upon TA. But we know that our PB is equal to half of PA by half of PA. So we can write this equal to PA by 2 divided by TC is equal to PA upon TA. And this PA and PA cancels out, so we get from here that our TC is equal to half of TA. Okay. And now let us go for PV diagram. This was with respect to our PT diagram. Now we go for our PV diagram. And once again we can just so we have our pressure and we are having our volume. So we start from a certain point A, and this point A we are having pressure PA, VA and temperature as TA. Okay. And it is given that isothermally expanded volume becomes twice. Okay. So we can expand it. And we get this point is our B, and here B, our pressure is our PB, volume becomes twice of A, and temperature is still our TA. Now it comes to our C, because pressure is our same, so this C is going to have our PB, and volume is our initial volume, that is our VA, and temperature is our TC, and it is back to its original position. So this is basically our PV diagram. Okay, and yeah, so there is no need too much of the explanation here, because it is straightforward based on our in the question itself it is given, everything is given. Next question. It states that two moles of helium gas undergo a cyclic process as shown in the figure. Assuming that gas to be idle, calculate the following quantities in this process. Okay. 1 second. I think okay, I forgot to do part B. Okay. And we have to find out the net work done. So for part B, and part B, the important thing here is that it comes to the original position in both our PT as well as PA in PV diagram. Okay. So we can say that the system returns to its initial state. Or we can say it is basically a closed cycle. And for this closed cycle, our internal energy change will be equal to 0, and our net work done will be equal to our Qnet. Okay, because as per our first law of thermodynamics. So let us find out net work done, that is net work done by the gas. Net work done by the gas W net. So first process is our isothermal. So you can see our process 1 is our isothermal. So because of this, the work done is, suppose W1, that will be equal to nRTA, and natural log of final volume, that is twice of our initial volume. So this comes as our 3 moles are given. So while the Fn is 3, so this comes as our 3RTA, and this comes the natural log of 2. And we have process second. Process second is our constant pressure compression. Constant pressure compression. So if its work done is suppose given as W2, which will be P delta V, and P is our, we already found out, is our PA by 2, and this comes as VA minus twice VA, and this is equal to our minus PA VA upon 2, or this can be also written as minus 3R, and this is our nRTA, and divided by 2, because PV is equal to nRT. Basically we have used here, we have used that our PA VA is equal to nRTA. So based on this we can easily get this equation. Now we have our third process. Process 3 is our constant volume. So W3 will be equal to 0. Thus we can say that our net work done, W net, will be equal to W1 plus 2 plus 3, and this comes to us as 3RTA, natural log of 2 minus 3 by 2 RTA, natural log of 2 and we can just take some things as common, so that will be giving us, this will be equal to, we can write this as our 3RTA, and we have natural log of 2 minus 1 by 2. So this is our net work done. Next question. It states that two moles of helium gas undergo a cyclic process as shown in the figure. Assuming the gas to be ideal, calculate the following quantities in the process. First is net change in heat energy, net work done, and the net change in internal energy. So basic diagram is given to us. So process starts from A and it moves to B, and there is a constant pressure of 2 atm. from B to C, it moves with respect to our constant, you can say, temperature. Then C to B, it is once again at constant pressure, and then it is from D to A, once again at a constant temperature. Okay. So basically it is we have our isobaric and isothermal process. So we start with the AB. AB is our constant pressure, that is our isobaric. You can see from A to B, which is our isobaric. And therefore its work done let us call this as W1 will be equal to P V2 minus V1, or in terms of ideal gas equation we can write this as our NR T2 minus T1, because temperature are given to us. So we can write our W1, N is our 2 moles, R is 8.314, and T2 is our 400 minus 300, and this gives us 1160 joules. Now we come to our B to C, which is our basically isothermal process. So we have our B to C, and this is our isothermal process. Therefore we can write that the work done, suppose that is our W2, that will be equal to NR temperature at C and log of our V2 by V1, and V2 by V1 we can replace it by P2 by P1. So we can say this is our NR TC, and we have this as log of P2 by P1, and we know all these values, so we substitute them. We have this as 2 into 8.314, and this is our 400 Kelvin, and we get this is basically natural log. Let me correct myself. This is a natural log, and this is also a natural log, and we multiply it by 2.303, so this comes as log to the base 10, and this ratio is our 2, because P2 is our P1. One second. Yeah, so this comes as our 2, and we can write that our W2 will be approximately equal to 406 2.9 joules. And we have now from C to D, and once again it is isobaric, and we can write that our W3 will be equal to NR temperature at D minus temperature at C. Let me correct here also. This is our here, and here we have to write temperature at B and temperature at A, then it makes a little bit of sense. Here also volume at B and volume at A, and we simply substitute the values. We get this as 3 into, we have this as 8.314, and this is about 300 minus 400. So we get our W3 is equal to minus 1660 joules. Now we come to D to A. D to A, same process, and we can write, let us suppose the work done is our W4 is equal to our NR TD and natural log of PD upon PA, and this comes as, one second, PD by PA I think there is some mistake, PD upon PA, and this will be actually P2 upon P1. Yeah, this makes much more the sense. So we substitute the values, we get this as 2 into 8.314 and this is natural log of 2. So similarly we substitute the values and we get this at W4 will be approximately equal to 406.9. Sorry. This is our this will be coming as, let me correct myself, W4, this will be minus and then it comes as 2 into 8.314 multiplied by our 300 and multiplied by 2.303 and natural log of 2, sorry. Okay, otherwise it will be 1 by 2, so 1 by 2 we have taken as minus, so this comes as 2. Now it's correct. So we have W4 will be equal to minus 3452.2 joules. So we can have net work done that is our W will be equal to W1 plus W2 plus W3 plus W4. We substitute the values, we get this as our 1660 plus 4602.9 minus 1660 minus 3452.2. 1660 cancels out and we get the net work done W will be equal to 11507 joules. Now we come to the part B. Okay, we have to find out the net energy. We just dealt with our part A. So net energy, so we know that the first law of delta Q is equal to delta U plus W, and for closed loop, because it is a cyclic process, delta U is equal to 0. Therefore we get our delta Q is equal to W, which comes as 1170.7. Okay. And C part, net change in internal energy. So for, like we said, it is a cyclic process, so net change is equal to 0. So delta U is equal to 0. So we can say no change in internal energy. Next question. It was asked in the year 1992, and it states that a cylindrical block of length 0.4 meter and area of cross section 0.04 meter square is placed coaxially on a thin metal disc of mass 0.4 kg and of same cross section. The upper face of cylinder is maintained at a constant temperature of 400 Kelvin and the initial temperature of the disc is 300 Kelvin. If the thermal conductivity of the material of the cylinder is 10 watt per meter Kelvin, I'm not sure about the unit, might be wrong also, and the specific heat of the material of the disc is 600, how long will it take for the temperature of a disc to increase to 350 Kelvin? Assume for the purpose of calculation the thermal conductivity of the disc to be very high and system to be thermally insulated except for the upper face of the cylinder. So in this case we are given that so this involves two concepts. One is the principle of heat transfer and other one is thermodynamics. And we are going to start with a cylinder. So it says that upper face is maintained at 400 Kelvin. Okay. So you can say that upper face of cylinder, let us suppose its temperature is our TH and that is given to us our 400 Kelvin, and this will be acting as a heat source. This is basically our heat source. Okay. And the initial temperature of the disc let us call this as Ti, and that is our 300 Kelvin. Okay. And we want that the temperature should be 350 Kelvin, so we can say final temperature of the disc is our Tf, and that is equal to 350 Kelvin. And the length of the cylinder is given to us. Length of cylinder is suppose L, that is 0.4 meter, and its cross sectional area, let us suppose that is our A, that is 0.04 meter square, and mass of the disc is also given, and thermal conductivity of the cylinder is also given. So we can say that thermal conductivity of cylinder, let us suppose denoted as K, and that is given as 10. and we are having our disk. So mass of the disk, and let us suppose it is small m, which is 0.4, and specific heat is given. So we can say C is our 600, and it states that disk thermal conductivity is very high. So from here we can say that the temperature is uniform, or we can say there is no temperature gradient within the disk. Okay, the temperature will be uniformly distributed all around the disk. Okay. And it also says that system is thermally insulated except from the upper face of the cylinder. So which basically means that heat flows from the hot end through the cylinder to the disk. No heat is lost. So this is important here. So we are given that system is thermally insulated, and except upper face. And which basically means that heat flows only from the hot end through the cylinder to the disk. Heat flows only from hot end to the disk. So the top end, or we can say the upper surface, is only the heat source for the disk. There is no other source of the disk. So first of all, let us, you can say, find out the heat transfer rate. So we can say our heat transfer rate, and heat transfer rate is dq by dt, and this dq by dt will be equal to this is Ka, and temperature at the top minus temperature, and that comes as our length L. Okay. And this law is also called as a Fourier law for steady state condition. Okay, let me put it here. This is also called as a Fourier's law for steady state conduction. And we substitute the value, we get this our dq by dt will be equal to our 10 multiplied by area is our 0.04, and temperature, this is H not A. This is our 400 minus T, and length is our 0.4. So this comes as our 400 minus T. Okay. So it means the heat flow is our heat flow rate to the disk. Okay. So this is our heat flow rate to the disk. Heat flow rate to the disk is our 400 minus T. Now you can say the heat received by the disk causes its rise in temperature, and from there we can say the heat capacity of the disk. So you can say that heat received by the disk causes its temperature to rise. Therefore, we can say heat capacity of the disk, and which is denoted at capital C, will be equal to mass and its specific heat, that is C. So this comes as our 0.4 multiplied by 600. So this comes as our 240 joule per Kelvin. Okay. And we know that rate of change of internal energy is given as C dt by derivative of temperature with respect to time. So we know that rate of change of internal energy of the disk it is given as our C, capital C, and rate of change of our temperature. And since there are no losses, we can say that the heat rate of change of internal energy will be equal to rate of heat received by the disk, that is dq by dt, as there is no losses. Okay. And this dq by dt is our 400 minus T. And C we just found out, so we substitute it, we get this as 240, and we have this as the rate of change of temperature is equal to 400 minus T, and this gives us dt by T is equal to 400 minus T divided by 240, and this is nothing but our first order differential equation, which we can solve it. So we can write this as our dt by 400 minus T is equal to dt upon 240, and the temperature is from, we have to integrate. So initial temperature was our 300, final temperature is our 350, starting is our 0, and upper time, let us suppose, is our, you can say, tau, just a differentiation in order to differentiate with respect to simple T. And this gives us minus natural log of 400 minus T, and we have lower limit of 300, upper limit of 350 is equal to tau by 240. So we get this as minus natural log of 400 minus 350, and this comes as plus natural log of 400 minus 300 is equal to tau upon 240. And this is quite simple to solve. We can just put, we get our tau will be equal to 240 natural log of 2, which is approximately equal to 166.4 seconds. I think this was, yes, so only time was asked. So this here tau is the representation of time only. Okay, so this tau is nothing but about time. Next question. It was asked in the year 1993, and it states that an ideal gas is taken from state A, pressure P, volume V, to a state B, pressure P by 2, volume 2V, along a straight line path in a PV diagram. Select the correct statement or statements among the following. So basically this is a straight line. This is point A and this is point B. And okay, the straight line will be a little bit different way because the pressure is also going to change. So we start with something like this. So this is point A and this is point B. Pressure is PV, and here it is P by 2 and volume is twice V. Okay, so this kind of straight line is there. And in case of PV diagram, we can just represent like this. So this is our pressure and this is our volume. And we can say, we can find out the equation of this straight line. Equation of straight line in PV diagram. And we can say that here we are having point A. Point A is our pressure P, volume V, and we have point B. Pressure is our P by 2 and volume is our twice V. So from here we can find out the slope of the line, that will be equal to our P by 2 minus P, and we have this as twice V minus V. This comes as our minus P upon twice V. Therefore we can use the equation and point slope form x minus x1 is equal to m times v minus v1. And 1 second. Okay, we can say using point slope form, with respect to point A, and this point slope form, we can say that our because this P and P we have to differentiate, otherwise it will be little bit typical to solve it. Okay, let's make one of as dependent upon x, and that is going to help okay, so we can say that our P minus P will be equal to M, and let us call this as V minus V naught. V naught, when later on we can just solve it, because otherwise it will be coming as same. Here let us write, okay, let me write this as a P naught just to differentiate, otherwise it will be everything P and V and they cancel and it will result in a big problem. So from here we can say that our P is equal to, we have our P naught plus, and this will be our minus P naught upon twice of V naught, and we have a V minus V naught. Okay, we just converted this into form of our V naught, and for that let me correct it here also. This is our V naught, this is V naught by 2, and this comes twice of P naught. Okay, and pressure is, this is P naught, and this is P naught, and P naught, just in order to differentiate. Rest of things are going to follow itself. So we can say from here that our P will be equal to, this will be our P naught, and this is a minus P naught V upon twice V naught, this will be plus, and we have P naught by 2. Okay, so this comes as our 3 P naught by 2 minus, we have our P naught upon twice V naught times V. Okay, and we assume that our V upon V naught is suppose equal to x. Okay, therefore we can write that this pressure equation will be dependent upon x is equal to our P naught, and this comes as our 3 minus x upon 2. And obviously this is nothing but our linear equation. Okay, and we can just verify it also, so that this P naught and P get clarified. So we can say that at x is equal to 1, at x is equal to 1, we are having V is equal to over V naught. Therefore we can say our P is equal to P, this comes as 3 minus 1 divided by 2, so this comes as our P naught. So this P is equal to P naught, and similarly we can say at x is equal to 2, we are having V is equal to twice of V naught, Therefore we can say our P is equal to P naught, and this comes as 3 by 2 divided by 2, which comes as our P naught divided by 2. Okay, so this relationship is holding, so it means this equation is correct one. Okay, let us, you can say, discuss our all the options one by one. So we go with our option A. And option A states that work done by the gas in the process A to B exceeds the work done that should be done if the system were taken from A to B along the isothermal. So first of all, let us find out the work done along the straight path, which is our AB. So we have our work done along straight line path, and let us call this a W line. And work done by the gas, the standard formula is our W is equal to our V naught twice V naught, and this comes as P times dV. And we already know our P, so we substitute it. So we get that our work done because of the line is equal to integration V naught twice V naught, and P is our 3 P naught minus P naught upon twice V naught. So this comes as our 3P upon 2 minus P upon twice V naught times V, and this is our dV. And we know this is simple integration. In the first term we get this as our 3P by 2 times V minus P upon 2 V naught, and this comes as our V square. Limits are from V naught to twice V naught. And so we can write this as our 3P naught by 3P by 2. This will be upper limit is our twice V naught, and minus, and this comes as our 4 because of the V square. So we get this as our P upon 4 V naught, and this comes as twice V naught whole square. This is upper limit minus the lower limit, that is our 3P by 2 times V naught minus P upon 4 V naught, and this comes as our V naught square. And this entire solution will be coming as our, that is work done because of the line, will be equal to 3P times V naught divided by 4. Okay. And now we come to the isothermal path. Work done along isothermal path. And let us call that as a W iso. And So we can say that at states A and B, at states A and B, we can write our PV is equal to our P times V naught, or let me write it as a P naught just to differentiate, and this comes as our P naught is our P naught upon 2, and one second, pressure is P by 2, yeah, one second, this, yeah, so this comes as P by 2 and volume becomes our twice. And here 2 and 2 cancels out, so this is equal to P times V naught. And for isothermal, we can write our T is equal to P times V naught upon NR. Therefore, work done, work iso is equal to V naught twice V naught, and we have this as nRT times V, and this is our dV. And this is straightforward. We are having our nRT, and this will be natural log of V, and the limits are from V naught twice V naught. So we get our work done iso is equal to nRT natural log of twice V naught upon V naught. V naught cancel out, so this comes as natural log of 2, and nRT is our P V naught, and natural log of 2 is our 0.693. So we make a comparison. So work done of the line, this will be equal to our 0.75 P times V naught. Therefore, we can say that work done because of the line is greater than work done because of the iso. Okay, from the value we can write 0.75 PV naught is equal to 0.693 times V naught, not equal to but greater than. Okay, so statement A is true. So this statement is our true. A is true. Now we come to the statement B, and it states that in the TV diagram, the path AB becomes a part of a parabola. Okay. So we start with option B. And for TV diagram, it becomes part of our parabola. So we are going to use our T is equal to PV upon N times R. And we can substitute our P, and this gives us that our T is equal to 1 times NR, and this comes as 3P by 2 minus P by V naught, V and whole multiply by V. So we can take P as common. So this becomes a P upon NR is equal to 3 by 2 minus V square upon twice V naught. And we can write this as our T is equal to P upon 2NR, giving us 3V minus V square upon V naught. And we say let temperature at A is given as T naught, which will be equal to over P times V naught upon NR. Therefore, we get that our T is equal to, and this comes as our T naught upon V naught and 1 by 2, and this is about 3V minus V square upon V naught, and we multiply V naught inside, we get this as our T naught by 2 is equal to 3V upon V naught minus V upon V naught whole square. And let us assume that our V upon V naught is equal to X. Therefore, T is equal to T naught, and this comes as our, this will be our 3x minus x square upon 2, and so this equation is basically quadratic in x. So we have a equation that is quadratic in x, or x we can say in terms of our v. Therefore, we can write that our T is equal to a v square plus bv plus c. Okay. And we can write that our a will be equal to minus T naught upon 2 V naught square, b is equal to, we have our b 3 by 2 T naught by V naught, and our c is equal to 0. So therefore, you can say it is a equation of parabola. Therefore, B is true. So B is also true. We come to the option C. In the PT diagram, the path AB becomes a part of a hyperbola. Okay. So we start with option C. Option C, and we already know that our T is equal to T naught 3x minus x square upon 2, and we also know that our P is equal to P 3x minus 3 minus x upon 2. So we can write that our, from here we can say that our 2p upon p is equal to 3 minus x, or we can say that our x is equal to 3 minus 2p upon p. So we substitute x into our T equation. So we get our T is equal to T naught, and this is x we can take as so we get this as 3 minus 2p upon p multiplied by 2p upon p divided by 2, and this can be written as our T naught 3 minus 2p upon p, and this ratio, let us suppose this is equal to q is equal to p upon p. So we get I think I missed something here. 3 we can take x common, so this comes as 3 minus x into x. Sorry, let me correct this. It doesn't look good actually. think this is very complicated. Let me solve this again. I think it is. First part is more or less clear. The only problem is with our part B. Let me check. Let us solve this part B again, because this is very complicated. The answer is correct, no doubt, but this is getting more complicated. So we can say that slope of the line, that is our P minus P by 2, and this is our V minus twice V. It will be coming as 1 by 2 P by V. And if we use that, and this is equal to slope of line, let us suppose that is our M. Therefore, we can say that our P will be equal to minus twice V multiplied by M. Okay, now let us use our ideal gas equation. An ideal gas equation which gives us that our PV is equal to nRT, and so we substitute value of P, we get this as minus 2V multiplied by slope, and V is equal to nRT, and we open the bracket. So from here we get that our V square is equal to, we have this as our nRT divided by minus 2, and M is our slope. And here everything is constant, so we can say that our V square is a constant term multiplied by temperature T, and this is nothing but equation of parabola. Okay, I think this approach is much better, otherwise it is getting lost in P and P and P and P. This is P, this is P, and this is making a mess. Sorry for that. And so part B is correct, which we already proved also, but now we come to the PT diagram. So option C, and we already know that this equation, that is our P is equal to minus 2V times M. And once again, from here we can say that our V is equal to P upon minus 2 times M, that is the slope. And we have our ideal gas equation, that is equal to PV is equal to nRT. So we substitute value of V, so we get this as P is equal to P upon minus 2 times M is equal to nRT. So we get this as our P square is equal to minus 2 times slope nRT, and this we can also write up a P square is equal to a constant multiplied by T, and this is also our equation of parabola. Okay, and option C, I think it states that it is a hyperbola, so option C is incorrect. Option C is incorrect. Okay, now we come to the option D, and option D states that in going from A to B, the temperature T of the gas first increases to maximum value and then it decreases. Okay. So we know the expression for our temperature. We can say option D, and option D we know that our Tx will be equal to our T naught x 3 minus x upon 2, and for we are simply going to differentiate it with respect to x, so we get this as dt upon dx is equal to T naught, and this comes as our 3x, so this will be our 3 minus x square, so this comes as 2x divided by 2, and for maximum we are going to put that our dt by dx is equal to 0, and so we get that our 3 minus 2x will be equal to 0, giving us x is equal to 1.5, and x is nothing but our ratio of v upon v naught is equal to 1.5. So we get that v is equal to 1.5 times v naught. Now we find out the second derivative. Second derivative, we get double derivative of our with respect to x will be equal to, this comes as a T naught, and this will be minus 2 upon 2 is equal to minus of T naught, which is negative, that is less than 0. So it means at x is equal to 1.5 we are going to have maximum. We can say that at x equal to 1.5 we are having T naught will be our maximum, and suppose T naught will be maximum, and that will we call that as a T naught max. So we can find out this value of T naught max. We get our T naught max will be equal to our T naught, and this comes as our x multiplied by 3 minus x, and we are having this as 1.5, 3 minus 1.5 divided by 2. which gives us 1.125 times T naught. Okay. So it means that for x is equal to 1, x is equal to 1, we are having our T is equal to T naught, and this T increases to 1.125 times T naught, and at x equal to 2, T is equal to T naught. So it once again decreases. Okay, so it will be something like this. It increases, then it decreases. So option D is also correct. Is correct. So we have option A, B and D are correct. C is wrong. Next question. It was asked in the year 1993, and it states that 1 mole of monatomic ideal gas is taken through a cycle shown in the figure. A to B is adiabatic expansion, B to C is cooling at a constant volume, C to D is adiabatic compression, and D to A is heating at a constant volume. The pressures are at A and B are denoted as PA, TA, PB, TB, etc. respectively. Given that TA is 1000 Kelvin, PB is 2/3 of PA, and PC is 1/3 of PA. Calculate the following quantities: work done by the gas in the process A to B, heat lost by the gas in the process B to C, and temperature TD. Basic figure is given to us. Okay. So let us write all the data that is given to us. We are given number of moles, that is of 1 mole, value of N is equal to 1. And we are given that it is a monoatomic gas. Monoatomic gas, so we can say this is equal to our 3/2 times R, and our Cp will be equal to 5/2 times R, and the adiabatic index is equal to 5/3. And temperature at A is given, TA is our 1000, and the relationship between the pressure is also given. Our PB is 2/3 times PA, and PC is also 1/3 times PA. First we come to A to B, that is our adiabatic expansion. So we have our from A to B, it is our adiabatic expansion. Therefore we can write that temperature, pressure, and we have this as 1 minus gamma upon gamma is equal to constant. And we can write from here that our TA, PA 1 minus gamma upon gamma is equal to TB, PB 1 minus gamma upon gamma. So our TB is equal to TA, and PB upon PA, and we can write this as our gamma minus 1 upon gamma. We just changed from 1 minus gamma to gamma minus 1, and this will be giving us 1000, and PB is 2 by 3 times PA, so this comes as our 2 by 3 PA upon PA, and gamma minus 1 upon gamma will be 2 by 5. P and PA cancels out, so this comes as our 1000, 2 by 3 and 2 by 5. So we get our TP is equal to 1000 into 0.85, which comes as 850 Kelvin. Now we come to the work done by the gas. Work done by gas from A to B will be equal to our C of V, and this comes as TA minus TB, and we simply substitute the values. This will be equal to 3 by 2 times R, and we have this as 1000 minus 850, and R we already know. Okay, let R we can just substitute later on. This will be coming as 225 times R, and if you substitute value of R also, so this will be approximately equal to 1870.2 joules. Now we come to B to C. B to C, that is a constant volume cooling. So we have our volume is constant, volume, therefore volume at C will be equal to volume at B. Therefore we can write the equation that our T upon C upon T upon B is equal to PC upon PB, and PC is our 1 upon 3 PA, and this is our 2 upon 3 PA. A and A cancels out. This comes as 1 by 3 multiplied by 3 by 2. 3 and 3 cancels out, so this comes as 1 by 2. Therefore we get TC is equal to TB by 2. TB is our 850 by 2, giving us 425 Kelvin, and constant volume we can say, or rather we can say we know that work done is equal to 0 at constant volume. Work done is equal to 0, therefore our Q is equal to delta U, which is our C of V times TC minus TB, and this has to be less than 0 because of cooling. So heat lost by the gas heat lost by gas will be equal to minus of Q is equal to C of V, and this is our TB minus TC negative, which is simply multiply it, and we get this will be equal to our 3 by 2 times R, and we have 850 minus 425, and this gives us 1275 upon 2 times R. And okay, let's substitute value of R. This comes as a 1275 multiplied by 8.314 divided by 2, and let me calculate it. This is 1275 into 8.314 divided by 2. 1275 divided by 2, and this comes as second. Well, let us keep it this way also. I think we'll solve this. I think it's required or not required. We'll see to it. And then we come to our C to D, which is adiabatic compression. Compression. I think there is some four to 5, 3. Looks good, I think. Okay, let's see. And C to D is our adiabatic compression. this was correct. So this comes as our 5279.63 joules. Now we come to A to B, that is our adiabatic compression. So we can write that our PA gamma minus 1 multiplied by TA minus of gamma is equal to PB gamma minus 1, and we have TB minus of gamma, and this can be written as we can take the ratio of the pressure. So we get PA upon PB gamma minus 1 is equal to TA upon TB whole raised power gamma, and heat lost. Okay, we found out heat lost, no? Yeah, we found out heat lost. So this is our, we have to find the temperature TD. Okay, and we have our path BC, sorry, so this is for path AB. Similarly, we can write for path BC, and path BC is going to give us that P of B upon T of B, because BC is, I think, constant volume. Yeah, it is a constant volume. So we get P of B upon T of B is equal to PC upon TC, and from here we can say that our PB upon PC is equal to TB upon TC. Now we come path CD. Path CD, we can write that our PD upon TB gamma minus 1 will be equal to power path CD, sorry, we can write that our TD will be equal to over TC times VC upon VD gamma minus 1, which gives us that VC by something missing. Let me do it again. I messed up big time today. Sorry for that. Okay. So from A to B, we can write that our VB upon VA gamma minus 1 will be equal to TA upon TB, and this comes as about 1000 upon 850. I think this is temperature at T. D2A is at constant volume. Okay. Yes. So we start with path of AB. We are going to deal with this temperature point of view because then it will be easier to substitute. Okay. So we can say for path AB, can write this as P of A gamma minus 1 T of A minus of gamma is equal to P of B gamma minus 1 and T of B minus of gamma. So from here we get that our PA upon PB gamma minus 1 is equal to TA upon TB raised power gamma. And so this is A, B, C and D. This is almost straight. Okay, so pressure is PA, PB, PC, PD, and they are having same volume here as well as here. Okay, 1, 2. Okay, now we come to the path BC. So we can say our path BC will be equal to our constant volume is there, so we have PB upon PB PB upon TB is equal to PC upon TC, and this can be written as PB upon PC is equal to TB upon TC. Now we come path CD. So we can say for path CD we get this as our PD upon path CD is adiabatic compression, and okay, path CD is adiabatic compression and path AB is adiabatic expansion. Therefore whole raised power gamma minus 1 is equal to TD upon TC whole raised power gamma. Now we come to the final path, that is our D to A. D to A is our PA upon PD is equal to TA upon TC. So we can just multiply them and we get PA upon PB multiplied by PC upon PD whole raised power gamma minus 1. This is our, let me call this equation number 1, 2, 3 and 4. So we have our, from equation 1 and 3, from equation 1 and 3 we get PA by PB divided by PD by okay, this has to be PC. So now it looks good. So this comes as our PD by PC. And this is about gamma minus 1 and this is also our gamma minus 1. So this comes as a PC and we have this is gamma minus 1 is equal to, we have this as TA upon TB whole raised power gamma and TD upon TC whole raised power gamma. Okay, so if we get this as our PA upon PB multiplied by PC upon PD gamma minus 1 is equal to TA upon TB multiplied by TC upon TD whole raised power gamma. And now we deal with our equation number 2 and 4. So you can say from equation 2 and 4. 2 is our PB upon PC. So we have PB upon PC divided by PA upon PD is equal to and we have this as TB upon TC is T and this is our TB upon TC and we have this TA upon TD. Okay. And this can be simplified and we can write this as our PB upon PA multiplied by P upon PC multiplied by PA upon PD is equal to TB upon TC multiplied by TA upon TD. And we know that Okay, let us make this left side same. So let me write it correctly. I'm going to write this as PA upon PB and multiply by PC upon PD is equal to TA upon TB and TC upon TD, and whole let us take gamma minus 1 and gamma minus 1. So our, let us call this equation as equation number 5 and this as equation number 6. So we can say from equation 5 and 6, 5 and 6, left side is our same. So we get from here that our TA upon TB multiply by TC upon TD whole raised to power gamma is equal to TA upon TB multiply by TC upon TD whole raised to power gamma minus 1. So we can just modify it, and this can be written as TA TC whole raised to power gamma TB TD whole raised to power gamma is equal to TA TC gamma minus 1 and TB TD gamma minus 1. And let us swap the ratio. So we can write this as TA TC gamma divided by TA TC and gamma minus 1 is equal to, we get this as our TB TD whole raised to power gamma divided by TB TD gamma minus 1. And so we can just, okay, now it's quite easy to solve now. We get this as TA TC, base here same, so this comes out gamma minus gamma plus 1 is equal to TB TD, and we have gamma minus gamma plus 1. Gamma 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 cancels out, so we get TB TC is equal to, sorry, TA TC is equal to TB TD, and we need to find out TD. Finally, so we get this TD will be equal to TA TC divided by TB, and we get this is TD is equal to, we have our TA that is given to us as 1000, TC is our, we just found is 425, and TB is our 850. This gives us that our TD is equal to 500 Kelvin finally. Okay. Oh. So it was all calculative part except Yeah, I think, sorry for messing up all these questions, but finally we were able to get the solution. And so this completes all the 5 questions. There were 2 questions from the year 1993, 2 questions from 92, 1 question from 91. So this completes all the 5 questions. Thank you.